Every day, billions of people use smartphones without realizing that. Inside this small device exists one of the most incredible engineering achievements humanity has ever created. Hidden beneath the glass, cameras, and familiar components is a tiny chip smaller than a fingertip. But when we zoom deep inside this chip, we enter an entirely different world. A world filled with billions of microscopic transistors, tiny electronic switches turning on and off billions of times every second. They process everything you do, every photo you capture, every video you watch, and even the massive artificial intelligence systems changing the world today. But there is one question: how can humans create something this incredibly small? The answer lies inside one of the most complex machines ever built, the EUV lithography machine, a giant system weighing more than 100 tons, containing hundreds of thousands of precision components, costing hundreds of millions of dollars, and a machine so advanced that almost no country in the world can build one completely on its own. But why does a tiny chip require such a massive and complicated machine? For decades, humans have been trying to make transistors smaller and smaller. The more transistors we can place inside a chip, the more powerful, faster, and more energy efficient that chip becomes. But eventually, these structures became so small that traditional manufacturing technology started reaching the limits of physics. Humanity needed a completely new method, and this is why EUV technology was created. When the outer layers of this machine are open, inside is not a normal mechanical system. It is a world of extreme precision engineering, a system where every movement, every vibration, and every microscopic change must be controlled. Inside the EUV machine are vacuum chambers, advanced sensors, robotic systems, optical modules, and thousands of components working together with almost impossible accuracy. Because at the nanometer scale, even a tiny particle of dust can become a massive problem. The process begins when a silicon wafer enters the machine. Robotic systems carefully move the wafer without human contact. The wafer is placed onto an extremely precise moving platform called the wafer stage. This system can move at incredible speed, while maintaining accuracy measured in nanometers. But the real secret of EUV technology is hidden deeper inside the machine. The light source, one of the most difficult light systems humanity has ever created. Inside a vacuum chamber, thousands of microscopic molten tin droplets are fired every second. Each droplet is smaller than the width of a human hair. At the perfect moment, a first laser pulse hits the tiny tin droplet and changes its shape. Immediately after that, a powerful CO2 laser strikes the same droplet with extreme precision. In a fraction of a second, the tiny piece of metal transforms into plasma hotter than the surface of the sun, and from this reaction, a special type of light is created. Extreme ultraviolet light, known as EUV, with a wavelength of only 13.5 nanometers, small enough to create structures that older technologies could never achieve. But creating EUV light is only the first challenge. The much harder problem is controlling it. EUV light is extremely difficult to work with. Almost every material absorbs it. Even normal air can block it. Traditional lenses cannot be used to control this type of light. So engineers had to create one of the most precise mirror systems ever made. These special mirrors are built from dozens of ultra-thin material layers. Their surfaces must be polished with almost unimaginable accuracy. Even the smallest imperfection can affect the entire process. These mirrors guide EUV light through the machine inside a vacuum environment. After traveling through the optical system, the EUV light reaches the reticle, a special mask containing the design of billions of transistors. The machine reduces this incredibly complex pattern and projects it onto the surface of the silicon wafer. But the wafer cannot stay still. It moves at extremely high speed. Inside the machine, the positioning system constantly adjusts its location thousands of times, while maintaining accuracy at the nanometer level, a level of precision almost impossible to imagine. Layer by layer, the invisible patterns begin forming. Silicon structures, transistor gates, insulating materials, and microscopic metal connections are created. After hundreds of manufacturing steps, a normal piece of silicon becomes one of the most complex objects ever produced, a modern processor chip. When we look at it with our eyes, it appears as a small piece of material, but deep inside, there is an entire microscopic world, filled with billions of transistors working together every second. These tiny switches are responsible for almost everything in our digital lives. The smartphone in your hand, powerful computers, massive data centers, and the artificial intelligence systems shaping the future. But what makes EUV technology even more incredible is that it cannot simply be copied. An EUV machine is not just a single invention. It is the result of decades of research across physics, optics, materials science, and precision engineering. Thousands of specialized companies contribute to creating the components inside this machine. From advanced lasers, to the world's most accurate mirrors, to mechanical systems moving with nanometer precision, every part must reach the highest level of engineering. All of this effort exists for one purpose: to control a beam of invisible light and use it to build structures smaller than anything our eyes can see. Inside the small devices we use every day is the result of one of the greatest engineering achievements humanity has ever created.